I'm actually really excited to present about this today because I actually have 2 manuscripts and a conference presentation about this, and I've never really talked about this in public ever, except for that one conference presentation, and that only had a very narrow amount of the work that we did. So I'm very, very excited to be talking about this today. So as you guys already heard about me a little bit, I included this slide in here because I know that Melissa was going to be reading my bio, but so actually, they actually asked me this on the way over here today, but I think it's kind of fun how I ended up here a little bit. So when I was an undergrad at the University of Cincinnati, we did the cooperative education program. So we had to spend 5 semesters in classes or in an internship experience in addition to doing 8 semesters of coursework experience. And it was because of that internship experience that I actually started to really enjoy geotechnical engineering and actually got very excited about the prospect of going to grad school. And then when I was in grad school, I actually had full intentions to go back into industry, but the project that I was working on at the time, I thought was incredibly cool, which part of it is what I'll be talking about today. And I think that there's a lot of really great research questions related to that we can still try and answer today. So as Melissa said, I sit over in civil and environmental engineering, but the reason that I'm giving this seminar here today is I also have an appointment over here in ocean engineering. And so what might be of interest to a lot of you guys is that I teach a marine geotechnics course, and it won't be offered next year, but it should be offered in subsequent years. So if anybody's interested in learning more about that, I will be teaching that in the future years. And then I also teach the design of ocean structures course over here in the spring semesters. So you guys, for those of you that are new grad students, will be seeing me a little bit more often. And then hopefully next fall, I'll be working on developing a remote sensing course with some mostly onshore applications, but there might be some interest into the coastal world about that as well. So I also have posted up here my research directions, but those were also already talked about, so I'll go ahead and skip that as well. So moving into the actual presentation today, I'm going to first talk about the background behind the work. So why did we end up doing this? Some of our data collection efforts, which has a lot of fun associated with that one. Some of the analysis and initial results that we have, and then there's quite a bit of future work, like I mentioned, that I think we can build off of what we had originally saw in this study to be able to move forward into new directions. So this entire project is sponsored by the Office of Naval Research, so it does have a little bit of a military twist to it. And in this project, we were specifically interested in looking at, can we assess soil trafficability, or basically the ability to drive onto any type of soil using remote sensing technology? Because when you are in some sort of covert or remote location, we can't go out and do physical ground measurements to go characterize our sites. We actually want to be able to predict, is our soil strong enough? What's our soil type? Are we able to go drive on it simply by looking at some sort of satellite image? So when I talk about trafficability, there's 2 separate processes that we need to look at. That's going to be your bearing capacity failure, which is basically, can your vehicle actually drive upon or go onto the soil without sinking in? And then we also have our traction. So can your vehicle actually get started once it's into the soil? The one that we primarily focused on looking at is bearing capacity, because this is the one that causes us the most heartache and the most problems. So I have a picture that's actually shown here on the slide of this little vehicle on the beach in the Outer Banks of North Carolina. We were at the U.S. Army Corps of Engineers facility down there. And so in this situation, even though we got our vehicle stuck and it was awful, we were able to just go get help from all of our collaborators up at the facility up here. And they could come tow us out in about 5 minutes. And it was absolutely no big deal. We were like the 5th person over the course of this entire project to actually get stuck in the soil. They didn't really care. But when you're dealing with some sort of covert operation or in some sort of disaster response situation, such as like what's currently happening down in Florida, we simply cannot rely upon having somebody there that can come tow us out and come get us out of this disaster situation. So that's why we wanted to be able to do this remotely, is so that we could come up with some sort of framework to do this using remote sensing technology to be able to remain in a safe situation. So the primary focus of this project was on quartz sand sites, since that is the dominant soil type that you'll see around the world. However, living in the coastal worlds do know simply that we are not solely composed of quartz sand sites. We have things such as muds, gravels, volcanic sands, and carbonate sands, and these all have their own separate intricacies associated with them when they're trying to predict what the bearing capacity is. But the one that I'm going to focus on today is our mud sites, because that's what we did in this particular project. So when we talk about sands, typically we're looking at characterizing our strengths related to things such as our grain size, our relative density. So that's looking at how tightly packed all of our grains are to one another, as well as looking at things such as our friction angle, which helps characterize the actual strength of it. However, when we start talking about muds, we cannot use what we use for sands to classify the strengths. So we're looking at things such as settlement, which is basically how much our soil is going to compress when we drive upon it or when we move across it. And we look at this both at how much settlement is going to happen as well as how fast it's going to happen. That's also of interest to us. And generally, I'm going to group those together and they're bolded as our consolidation characteristics. And then the other one that we look at is what our undrenched shear strengths are, which is how we quantify the shear strength of our soils. However, as I have shown down here on the bottom of this slide here, is that we don't actually know what the magnitude or the variation on these characteristics are for these muddy sites. So that's kind of the impetus behind all of this work, because before we can actually go quantifying the strength of our sites from satellite data, we need to actually have an understanding of what the strengths of the sites are through some sort of in situ or laboratory measurements. So what we did was we came up here to the Great Bay Estuary to do field work, because the Great Bay Estuary, if you guys aren't super familiar with it, we're up here in Durham, we were working down here. There's a significant amount of tidal flats that are exposed at low tide. So this actually gives us a lot of different areas to be able to look at and actually very safe access to a lot of these sites. I have shown here in quotes the marine geotechnics playground, because you also not just find muds around here, but you can find gravel and sandy sites as well. So it gives us a lot of different variation, a lot of different sites that we can look at to characterize. And so what we did was actually, I will preface this by saying originally we had planned with Tom Littman to come up here in 2020, the summer of, to come do a huge field campaign with multiple people from Virginia Tech and use a lot of the resources here at UNH and also look at a bunch of different flats. But as we all sadly remember, COVID 2020 or 2019 happened that summer. So we had to really pare back what we were doing and actually just do an initial survey at this one site, which is at Adams Point, which is located near the Jackson Estuary Lab. I have a hard time saying that word, I apologize. And so we actually ended up doing sort of a preliminary study to look at how do we actually go about measuring these characteristics instead. So we did that study in August of 2020 because we got permission finally to come and do this. And so we did some initial studies at that Adams Point site, like I mentioned. So in our sampling that we did, we found that there was about 89% fines at this site with about 11% coarse material. And we have a wide range of geotechnical characteristics we found here, which things related to our liquid limits and our plastic limits. And using those parameters, we were able to classify this as a silty soil. So during our surveys, we had sort of two different techniques that we used to perform our measurements. We collected a series of soil samples. They're 10 centimeters tall. So we were able to push them in and pull them out and get pretty good lab samples. And then we also used a device called a free fall penetrometer. I'll talk about what that is in a couple of slides because it takes a little bit of explanation. But what this gave us the opportunity to do was to co-locate this free fall penetrometer with our soil samples, because we can derive a lot of our soil properties of interest from this device. And we typically have a lot of issues in most settings for collecting the samples to correlate to it, because this is intended to be done in water. And you can have a lot of disturbance and a lot of washing away of your samples as you're pulling it up through the water. And then the other thing I wanted to point out is Tom came up with a really fabulous way for us to walk out onto the mud. So these are essentially just pieces of plywood with pool noodles stapled to the bottom of it. And then they also have ropes attached to it. So we didn't have to worry about actually digging them up ourselves. We could just leave the ropes exposed and then we could pull them up or drag them away. And we were actually pretty stable, I will say. It looks a lot more stable, or it is a lot more stable than it looks. And I'm also happy to report that nobody fell in, which was a huge accomplishment for us. We were very nervous someone would fall in. So we also did a bunch of laboratory testing. So because of COVID, we couldn't do any laboratory testing here at UNH. So we took all of our samples, put them in a cooler and drove them back to Virginia. And so we did things such as vein shear testing, which is probably the most common thing that we do for marine soils to test their shear strengths. So essentially what that is that we push this little vein here. It's a little hard to see in these pictures. We push that about 5 centimeters into our soil. And then we have a crank that we crank up, and we're loading a spring until it could no longer resist against the soil. And then there's deformation on this gauge that we're reading. And then we can figure out what our undrenched shear strength is from this gauge that we're reading. This is what those springs look like that we're loading up to be able to shear what our soils are. And then the other thing that we did was a series of consolidation tests. So basically what this is that we have our soil that's placed inside this device right here into a little ring. And then we load it up with a series of loads to be able to measure how much it settles and how fast it settles over time. So what we're interested in measuring is both those, how much settlement and how long the settlement will take using this particularly laboratory test. And so what we're measuring specifically that's of interest to us in this study is the C sub V, which is our coefficient of vertical consolidation, which is basically just a measure of how fast our settlement will occur. The second thing that we did was all of our in situ testing. As I mentioned before, we had this device called our free fall penetrometer. And so this was originally designed for offshore environments, but we've been doing a lot of work fairly recently regarding using this to characterize things such as sand beaches, and also in our case, tidal mudflats. So what this is that it free falls through the air and then impacts the soil. When it impacts the soil causes it to slow down, and then we can, the device houses a series of accelerometers inside of it. And so then we can take the acceleration or deceleration, use the time that it takes for that to occur, and then integrate to get velocities and then to actually get into some sort of force. This also measures our pore pressure response because we can use pore pressures to actually help us look at our different soil types. So we measure our pore pressures through a filter ring that's shown right here. And that's what's called the U2 position. I'm not really going to go into what that means because there's different locations upon the penetrometer that this pressure element can be located. And all that does is change some of the processing techniques that we use to be able to actually extract usable data out of this. So then once we actually go about measuring what our sediment resistance force is, we can then know the area that the penetrometer that's in contact with the soil, divide that sediment resistance force by our area to get some sort of bearing capacity. And we call this a dynamic bearing capacity because soil strength is extremely dependent upon the rate in which it's sheared. So we can't call that a typical bearing capacity of our soils. So then be able to then convert from this dynamic bearing capacity to a more static bearing capacity that we can use. We use a strain rate correction factor. And this is related to the soil type. And so what I have shown here on this slide is just one specific example of how we can go about correcting for those strain rate effects. There's a couple different ways available in the literature, but this one's pretty common. And this relates our impact velocity that we measure to some sort of reference velocity. We use one that goes at a rate of 2 centimeters per second. And then we also have a soil dependent empirical coefficient that we use in this equation to be able to actually convert our dynamic bearing capacities to our quasi-static bearing capacities. And so then what I mentioned here is that then we can take our measurements of our quasi-static bearing capacity to measure our undrained shear strengths, and then data related to our pore pressures to get our consolidation parameters. So this is showing here just an example of what this data typically looks like. So this is going to be our deceleration with depth. It's going to be this solid black line here. And so as we can see that as we're going down through the soil column, we actually get stronger and stronger soils as we go down with depth. And then we can see what our velocity profile looks like, where we have our highest velocities up here at the top. And then we see that they decrease as they go into the soil column. And then finally, we can use those measurements to be able to calculate what our bearing capacities are. So we have our dynamic bearing capacities shown here in this pink line. And then we can see that as we start to, and we can think of that, our dynamic bearing capacity as having a strain rate correction factor equal to 0. And then as we increase that strain rate correction factor, we can see that we start to have a decrease in what our measured bearing capacities are. So the ones that we're actually testing here, because the other part of the study is we don't know what's appropriate to use for these soils to use this particular device. So we wanted to study what strain rate correction factors are the most appropriate for these soils. And we used 0 and 1.5 because those are our lower and upper bounds that we could possibly use. So this shows just some of the typical profiles for the entire survey that we did. So this is all of the different measurements that we did. And what I think is particularly interesting is that when we look here at a depth of about 20 centimeters, above it, we see fairly consistent results for both our deceleration that's shown here, and then our dynamic bearing capacity that's shown on the other side. However, once we start to get lower than those 20 centimeters, we actually start to see a lot of variation in terms of what our strengths are. And we started to ask ourselves, why are we seeing something like this? And I'll actually touch on that here in a second. So now that we have our measurements of our quasi-static bearing capacity to get our undrained shear strength, we have to divide it by another correction factor. So as you can see here, it's starting to get really complicated. There's just corrections on corrections on corrections. So this is a cone correction factor, which typically varies between 10 and 12 for normally consolidated soft soils. So there is a range, depending on what type of soil you're dealing with, you get different correction factors, which just keeps things eternally interesting. So then when we tested our values of 10 and 12, because once again, we're looking at our upper and lower limits, we plotted our undrained shear strength profiles with depth into the soil profile for our 9 different stations that we tested during this particular survey. We also plotted onto these plots. These are these little X's here. I know they're a little difficult to see, but we have these little X's here, which represent our vein shear results. And those are plotted at a depth of 5 centimeters because that was how deep into our soil samples the little vein was penetrated into. And then we we could actually compare then what our laboratory measurements were to our field measurements. And so what's really exciting for plots such as A1, B2, D2, E3, E1 is that we actually have a pretty good match between what our laboratory measurements were and what our field measurements were when we look at that strain rate correction factor of 0. So we actually feel really encouraged that this is going to be a great method to be able to use to characterize other sites. So now we might be able to move on to beyond our individual mudflat to go look at other mudflats around to be able to get our range of characteristics. However, I want to point out here that for things such as A2 and B3, we can actually, A2, A3, and B3, that we actually don't have a really good match between what our measurements from the penetrometer were and our laboratory measurements. And what we expect that to actually be a result of, a couple different things is, one, if we hit shells or gravel when we were actually doing the lab tests in our samples, if you hit that, that's going to jump your strengths upward. And then the other thing that we suspected is that we might have disturbance in our soil samples when we took them back to Virginia, because even though we tried our best to keep them upright, not to jiggle as we moved back, I mean, it's still a 12 to 14 hour car ride. They could have shifted, gotten moved, just got disturbed. So we actually might see an increase in our strengths due to the self-consolidation of those soils as we move them back to Virginia. So I'm going to touch back onto why we see that layering part here, because we also see those results reflected in our undrained shear strength profiles. It's a little tricky to see, but I promise you that at deeper depths, there is actually a more rapid increase when you do the calculations of your strength increase with depth. And the thing that we suspect, based off of a study that was actually done here at UNH back in the early 80s or so, was that there are things such as ice that form over top of these mudflats that might be causing them to, during the winter months, that when they move in the spring months, they start to move the soil with them and actually erode an upper layer of that soil away, causing them to have a stronger layer underneath and then a fresh layer of soil that's deposited every single summer, spring, and fall to then have that cycle repeated annually. However, that's just our working hypothesis for right now. We need to actually do longer term measurements over different seasons to actually see if something like that's occurring. So now I'm going to move on to how our pore pressures look. And so this is a goofy thing as geotechs like to do. We really like to plot our pore pressures onto a semi-log scale or a square root with time scale, because otherwise you probably wouldn't see any sort of trends associated with these pore pressure responses. But how we let this happen is that we drop our penetrometer into the soil and then we just let it sit there for an hour. And then we come back and pull it up, and then we can actually then derive our consolidation parameters from letting it sit in the soil for an hour. So what we see here is that we see an initial increase in what our pore pressures are. And then when they hit that peak, that's basically when we hit our maximum pore pressure. And then they're going to dissipate off with time. And so the pressures are going to decrease as we go on with time. And this is actually, I promise you, fairly typical results for this piece of equipment. And the only thing out of here I wanted to point out that was a little funky is this whole oscillation pattern right here. So that was not expected. So we had to sit back and actually think, why are we seeing that? And what we ultimately decided is that due to we had dropped it off the side of that little mud road that we had developed. And so when we walked back and forth onto that, we think that we were influencing our soil properties and what it was measuring. So then what we do is, like I said, we like to do goofy things like plot our pore pressures on a square root of time scale. So we plotted those on that square root of time scale. Then through an extrapolation technique by this paper by Sully et al. In 1999, they extrapolate back that flat portion of this pore pressure curve. We get what's known as our initial pore pressure value. We get our hydrostatic pressures, and then we end up normalizing what our measured pore pressures are to get this parameter T50, which is ultimately what we're interested in, which that tells us the time at which 50% of our settlement has occurred. So if we have 2 feet of settlement, we're looking at the time in which 1 foot of settlement will occur. So what we can do with that is use this formulation by Tay and Holsby to calculate our C sub H, which is our coefficient of horizontal consolidation, because the way that the penetrometer sits in the soil, we're actually measuring horizontal consolidation, not vertical. Because if you think about soils, we don't have, if you think about permeability of soils, you have permeability in the vertical direction, you have permeability in the horizontal direction. So we're actually looking at, in a sense, permeability in the horizontal direction, not the vertical direction. So in this formulation, we're looking at calculating the C sub H value related to this T factor or T star factor, which that's the one that comes down to where that pressure element was located, the size of the penetrometer. And then the one that I want to mention quickly is this rigidity index, which is, there is a whole lot of research into what this value should be for different types of soils. And I'm really not going to touch on that too much today, except for the fact that it typically ranges between 50 and 500. However, it's been suggested over time that this should actually be much lower than this for these really soft soils, especially like what we're dealing with on these mudflats. So we also tried out a value of 10. And so what's a little discouraging is that when we did end up plotting those lab samples that we had measured, in theory, we would expect, let me take a step back there. In theory, we would expect our vertical and our horizontal coefficients to be fairly similar because they're related through those permeabilities. And then unless you have otherwise good evidence to tell you, this is typically going to be between 1 and 1.4. Unless you have extremely layered soils, so if you have things such as sand lenses or silt lenses within these samples, you're really not going to see too much range in what these and what that value is. However, we did, and so there's a couple of different reasons why we think that's occurring. The first is the fact that, as I mentioned, we have that layering with the soil, and so what we have is we're only sampling that upper 10 centimeters, but when we look down at that 40 to 50 centimeters, which is where the penetrometer is resting, we might have a mismatch in what our samples are telling us, simply because we might have different soils with depth than we do on the upper. Also, the other thing too is that once again, we could have had consolidation and densification of these samples that's causing them to have different results, basically. So then, based off of our results in 2020, we decided to come back for a second survey in 2021 because COVID allowed us to actually travel even more and bring more people with us so we could experiment on different sites. So we added 2 additional sites, which the one is called Woody, which is located right around the corner from where Adams Point is, and that actually has more fines associated with it. So we were looking at 89% when we were looking at Adams Point, and then when we talk about Woody, we actually have about 98%. And then we also had a lower amount of coarse material. And then what was interesting is that the soil classification was actually a little bit different. So that allowed us to have comparison between what different mud sites would be. We also went up to a site located actually in Elliott, Maine. It was called Mass Cove. And that site was a lot coarser, but what was really cool about it is that it wasn't just all coarse. We actually had a bit of a coarser zone, which had about 84% coarse material and 16% fine material, as well as what we dubbed our finer zone, which had about 69% fine material and about 31% coarser material. So let us also look at the variation within the individual flat itself. We saw that as we moved towards the center of our flat, we actually ended up with finer material. In this, we also performed some laboratory testing of vein shear here because we now had access to labs, as well as doing more sediment samples and moisture content measurements. However, we actually ended up not getting the penetrometer measurements due to some equipment malfunction we had while we were here. So that's actually something that we need to look at doing in the future, is actually going out and doing the penetrometer measurements at these different sites. So like I mentioned, we were actually interested in seeing, are we getting the sample disturbance as we travel back to Virginia? And so we did some laboratory testing here using a piece of equipment called the Soil Saber, which is called that because the handle of it kind of looks like the handle on a lightsaber. That's how they marketed it to us at the very least. And it has that the same band that we used in the lab associated with it. The only difference with this one is that it has a dial, or it has a digital readout for us. So it was a little bit easier for us to actually see what our strengths were. And so when we actually compared those measured here in New Hampshire, which is from the Soil Saber, to the ones that we measured back in Virginia, samples that were co-located with one another, we actually did see a little bit of an increase in what the strengths were for the samples measured in Virginia, which kind of gives us the indication that we might have some problems there with our sample transportation process, and we should probably do a little bit better either about transporting them or doing more testing closer to our sites. We also wanted to compare the variability between our sites so we can have different sites to be able to look at what are these strength properties. So I have plotted here our fines content and our moisture content. And what I think is particularly neat and actually holds up with what we should be seeing is that where we have higher moisture content, such as at our Adams Point and at our Woody site, we also have a higher percentage of fines. And then where we have lower water content, such as at that coarse zone of Mass Cove, we actually see a lower percentage of our fines content. So when we look at those relationships compared to one another, we see that there is actually a really excellent correlation between them. But what we're ultimately not interested in is what those moisture contents or that fine content are. Or we're interested in looking at what the undrained shear strength is. So what are those strength properties of those soils? And so we actually also see the same trend that we saw with the moisture contents, where when we have lower moisture contents, we have higher undrained shear strengths. And when we have higher moisture contents, we have lower undrained shear strengths. So here's the thing though, now you're probably wondering, why am I talking about all of this? So I'm going to go ahead and skip to this next slide because it'll make a little bit more sense when I talk about this. So what we ultimately, like I mentioned at the very beginning of what this presentation was, is that we're ultimately interested in, can we characterize sites from remote sensing technology? So the type of data that we look at specifically is called synthetic aperture radar, or SAR. And what these images are composed of is it's an intensity of the radiation that is backscattered. And this is referred to as the backscatter coefficient. So as these satellites orbit around the Earth, they transmit a signal down and then they bounce off the ground and some of that data comes back to our satellite. And so when we look at this image here, this is of the Great Bay Estuary. We have lower backscatter coefficients correspond to lower returns, darker colors, and then higher backscatter coefficients or higher returns and lighter colors. And so specifically, when we look at bare soils, so soils without vegetation or people or anything on them, the return of this backscatter is related to our water content and to our surface roughness. So as we saw on the previous slide, if we have a relationship between our water content and our undrained shear strength, and we also have a relationship between our water content and what our fines content are, we can plug that into different soil types to then maybe create some sort of classification scheme based off of the backscatter response of these specific images. So what we did was we ultimately, in addition to all of our field measurements, we also collected a whole range of satellite images. I have those images plotted up here. And so what we decided to do was extract the backscatter coefficient that composed of each of those flats. And then we ended up plotting those as histograms of backscatter coefficient. So what this allows us to do is that there's different properties we can calculate about these histograms to be able to help us maybe classify our soil types using these histograms. Because as we look at them here, you can see that there are distinct differences between what each of these are. So there's a whole lot of different characteristics you can calculate about them. I'm not going to go over this. I just included this in for completeness sake. But we're going to talk about two here today, which we're going to look at the mean value, which is basically just the average of your backscatter coefficient. And then we're going to look at this property called the entropy, which is just a measure of randomness of that specific histogram. So when we look at our mean plotted against what our means plotted for our specific sites, what we can see here is that we actually have some sort of distinction between what our fine sites are and our coarse sites are. I know there's not like a huge distinction between them, but there appears to us at the very least, seems to be some sort of trend that we can look at. And what was really cool is that didn't just happen in a vacuum. We actually saw that over a whole range of different image characteristics. I have one of those plotted here. So we can actually see where those little triangles for the coarser zone of Mass Cove are always going to be higher backscatter coefficients in comparison to what those were for our finer sites. So that gives us some sort of insight that maybe we'll be able to someday have a really great characterization scheme for these different soil types. We also looked at our entropy, and I actually draw a little X on that one all the time because we are not interested in that one anymore, simply because we already have a way to be able to differentiate between coarse sites and fine sites. So what we can do here is look at, are there trends between our three different finer sites to be able to come up with our characterization scheme? And I think that there is. So when we go ahead and plot those against one another, we can plot in a vertical line for our mean backscatter coefficient, and we can see we have our fine sites differentiated from our coarser sites. And then now we can draw in boundaries in between our three different fine sites to help us be able to characterize different soil types as well. The thing I always want to point out about this plot, though, is that I have these as dashed lines with little question marks on them because at this current point in time, we're just kind of guessing that this is where this goes. We can see that there's wiggle room in it, but we don't have that many data points associated with this. So in order for us to feel more confident with what we're putting in here, we would probably need to look at more data, basically. So now I just want to touch on the overall results, I guess, of this particular study is that we can use those free fall penetrometers to be able to characterize our tidal flats, and we actually get fairly comparable results for at least our undrained shear strengths when we're comparing this to the more traditional metrics that we utilize. We also feel like we feel better and more confident in what we distinguish as our geotechnical properties of these different tidal flats. And we also believe that satellite processing or satellite data can become a very powerful tool to look at characterizing these sites, simply because we can look at things such as linking our moisture content to our things such as our fines content to look at different soil types. So I just want to touch on here briefly because I think that the work that we did here I think is really cool, but I still think that there's a lot more that we can do to be able to improve upon our results. So looking at a more detailed comparison of our field and lab methods. So can we actually do more measurements here at UNH so that we can actually have a better comparison so that we don't have to have that disturbance in our samples as we transport them? We should also, like I mentioned before, do the testing of our remaining field sites simply because it would be really cool if we can compare these different signatures across different soils, as well as improve upon our characterization from the SAR data, just so that we can add more data into those plots. The other factor that I've already somewhat mentioned was our seasonal variability and strengths. What are those actual properties? How can we go about actually quantifying what changes our soils? So this could be things such as biological action, rainfall, or even those ice events that I mentioned previously. The other one that I actually thought of when I was here this past winter for my job interview was I was driving by the flats and I saw that there was snow sitting on them. And I was like, I wonder how that changes the satellite signals. So how do we actually bypass things such as snow sitting on these specific sites? And how does that influence our backscatter response? And then finally, one that I think is interesting that I have not really done a lot of research into, but I think has a lot of implications is for things such as vegetated sites. If we have a seasonal changes in our vegetation properties and we have seasonal changes in our soil properties, how do those actually go together to be able to look at what's changing the strength overall? So as I mentioned, this actually is the culmination of 2 different manuscripts in a conference presentation. These are currently sitting with my co-author who's reading them to be able to submit them at some point. Hopefully these will be published in the next year or so you guys will be able to read those and actually see the full details of this specific study. And then I just want to say thanks to all of you for listening today, as well as fieldwork does not ever happen in a vacuum. I don't know how many of you guys actually do a lot of fieldwork for your degrees, but it takes a huge village to be able to make this type of work happen. And so there was a lot of people at Virginia Tech, including my PhD advisor, Dr. Nina Stark, Tom Lippman and his group here at UNH for basically getting us out onto the mudflats. Especially, I want to shout out Yang because he did this with us, I think, the night before his dissertation defense. So he gets a huge shout out for that one. As well as Dr. Gayumi over in civil engineering. They let us into the lab to be able to do some of that testing. And then finally, last but not also our group down at the University of Miami who helped us with their image collection. But like I mentioned at the beginning, this project was sponsored by the Office of Naval Research. So a huge shout out for them because without our great sponsors, we would never be able to do research. So thank you. And if you guys have any questions, I'd be happy to try and answer them. Yes.
In trying to characterize the physical properties, of course, that's important, but it would seem to me that certain physical properties are more important than other physical properties. Did you do any sensitivity testing to say what is the characteristics that are the most important to get right?
So actually, that's a great question. So not for this, so in the sand characterization part, yes, there was a huge aspect of that actually, but for the mudflat soils, we're not quite there yet. So actually, I should have mentioned that this work's also being picked up by another PhD student at Virginia Tech, who's actually going to look into more things such as that. So
yeah, and part of the question is, I know from working with radar is really messy. You've got lots of speckle. You need high quality digital elevation models, and so trying to extract things out of the radar within the range, within the certainty that you might need for certain parameters, that could be tough.
Yeah, and it's not a trivial process, yeah, it's difficult to be able to look at it, and so because when you have things such as the radar speckle is why we ended up going with the histogram part of it, because then you can sort of wash out almost the speckle that's associated with it instead of having to go with an exact value associated, just because there is so much. I mean, I'm going to zoom back really quickly on that. I mean, there is a wide range of backscatter that composes these mudflats. So that's why we ended up going with more of that histogram approach for it, just because we could look at more than just an average value.
Thank you.
Yeah.
Let's kind of follow up on that. Like, it's very neat. What's the spatial resolution of the SAR? And even more importantly, just because of what you said, the speckle and all that, what's the size of your kernel that you're collecting the statistics
over? So these ones that are called Cosmos satellites are 50 centimeter resolution. So 50 by 50 or 50 by 50 centimeters, and the TerraSAR ones are down to 20 centimeter resolutions. And so the actual resolution of the whole, like the size of the whole image, I'm always asked that, and I always can never remember the exact dimensions, but it's somewhere on the order of like 5 to 5 kilometers, depending on the type of image that you're looking at specifically. And that's because these ones specifically are the higher resolution ones, so they come in a significantly smaller footprint associated with them. When you start to look at larger pixel sizes, they do come into larger spatial resolutions in terms of the whole image.
If you have pixels at a 50 centimeter resolution, when you calculate your statistics, you're doing it over a kernel of a window of some size. And what's that size?
That's a great question. I don't remember what the sizes of those were, because I was able to go in GIS and actually draw in polygons to go around my area, and I forget what sizes those ended up being. But they also vary too. I should also add that they varied a little bit based off of your tidal, your water level. So when we had higher waters, we got a much smaller area than we did when we had lower waters.
So you're using this SAR data to classify the different mud areas, I'm assuming. Do you think you'd actually be able to use these backscatter coefficients to get some of the bulk properties out of the soil?
Yes, at some point. So part of the reason that we were looking at SAR is that you do have a really in agricultural applications, you typically have a really good relationship between moisture content and your SAR backscatter. But then in those situations, you're looking at more of a static environment. You don't really have a lot of variation in terms of what your ground conditions look like in a given time. But when we have things such as, titles or sites that are exposed and not exposed by water on cycles every single day, if someone goes out there and runs around and puts their feet all over the soil, that's going to change it in comparison than if you had then when your water rushes over it multiple times, it smooths all of that out. So that's where we run into that problems, is that there's this complex interplay between the surface roughness and the moisture content at a lot of our sites. So ultimately, we had a really great success for our relatively good success with our sand sites looking at moisture content, but we're not quite there with our mud sites yet because the water tends to just blow out all of our backscatter response where we really don't see any sort of variation. Yes.
So I have two questions. One of them is a legitimate question. The second one's a little bit goofier. But the first one is when you're taking into consideration the moisture of your samples, but specifically working in like a tidally influenced area, did you sample all of the sites at the same point in a tidal cycle, or will you sample at one site during multiple?
Okay, that's actually a really great question. Because these salads, we have no control when they come. So these come at a fixed time every morning and every night. So we just kind of have to suck it up and deal with the fact that we're on different tidal cycles when those different images are collected. The thing that's particularly tricky about these sites is that since they are exposed and covered and exposed, I forget, I think it was close to plus or minus hour and a half to 2 hours that they would only be before and after a high tide before and after low tide that they would be exposed. So we couldn't really control how much we had exposed and not exposed during our images. Is essentially what that comes down to.
The second question is, this has me thinking, is there a scientific definition of what quicksand is?
Yes. I will defer the answer to that question to the two other people I know in the room who might have a better answer for that. So.
Quicksand is when you have a usually upward directed pressure gradient, so the water is flowing from within the sand up, and it'll push the sand apart, and so you just sink through it. And it's usually fairly constant, it doesn't fade. I don't know how long it'll last. It depends on the source versus an earthquake or I don't know, a well. No. So the big difference is this is mud, quicksand is sand. And then I guess whatever's causing it to be quick.
Vibrations.
Right. So
Increases the pore pressure.
earthquake, the big one. But if you put a pump in the ground and you pump the water up, that can also cause it to become quicksand.
It's Matt Florence, by the way.
Yeah. Yes.
Can I ask you a question? We've got lots of questions on my notes. Drainage of the water out of the mudflat tidal. How does that impact your measurements? and especially with the timing of the satellites. But also the drainage isn't uniform over the mudflat. There was some evidence of some, tidal.
So, okay, so there was a, okay, so I'm gonna just zoom on back here again. So the one thing that Dean and I actually discussed a little bit was about, so in this, what's kind of interesting, so those dashed lines on there, and I did not mention this, those dashed lines are our hydrostatic pressures based off of the, how deep into the soil our penetrometer is. And these are the pressure response as it goes, as it sits through time. And what was kind of interesting, and I believe that we saw this at a different site, is that our hydrostatic pressures were above what our measured pore pressures are, which intuitively doesn't make a lot of sense. But what we think might also be happening is that we are having some drying over that hour-long segment of time that's causing basically that's causing our soil to lose a little bit of moisture content. However, the issue with a lot of muds is that they have really low permeability. So it's really hard for that water to drain out of the soil completely out of those top layers, especially since, and I didn't show a good picture, actually, that one's actually pretty decent at showing it. We did have like these little like pillow structures almost. We really didn't have a great word to describe what these were, that were like sitting there with that water filled into it. So a lot of water like that has a really difficult time getting out of the soil simply because it just kind of sits there and can't drain out very easily.
Yeah, so that figure you just showed a second ago, which is the time series with the square of the time.
Yeah.
Is there a particular time when the satellite image came over? Would that matter if you're characterizing the soils? There's this instantaneous time when you had your sensor out.
I don't think we have a good grasp on that right now. I think that's something that we should.
The timing of when the image occurred, that it came over during the time that you're making your measurements.
Yeah, so I can actually speak on that a little bit better for the sand sites, because that was a huge area of debate that we always get for a lot of that, because that is almost more so impacted than these sites are, because you are dealing with the tidal cycle that's going in and out cyclically. So what is exposed, what's water covered, what is the actual moisture content at that moment? Because I'm only one person, I can't, and we were doing a lot of, even here, we're trying to do a lot of these measurements with a single person, which makes it, extremely difficult to get exact moments when the satellite is flying over. So that's also something that I was wanting to look into in the future.
It seems like it doesn't matter that much whether you walk on the mudflat as soon as it's starting to drop or after it's drained. It's still pretty much, you're just going to sink in it one way or the other.
Yeah.
So from a characterization perspective, it seems like you're looking at a bulk kind of measurement of what the satellite is trying to give you against when at some point you made your estimates of the bearing capacity. Is that right?
And that's what we came up with, I think, for the muds in the end, but we don't know if there is much of an impact, because we never really tried over the whole, 2.5, 3 hours, whatever it was that it was exposed, if there was any difference. But it didn't see, just walking on it, like you pointed out, it didn't really seem like we had much of a difference. The time scale of
change is much longer than that. Thanks.
So I actually believe it was your presentation last week where you talked about soil liquefaction. I don't remember if that's something that only occurs underwater, but is that like a consideration for this? And if so, and if not, are there any parallels you can draw in like the math or analysis between the two?
No, there isn't really a comparison, because the phenomena that Melissa and Matthew actually was just talking about only really occurs in sands due to the way, this gets really deep into it, but due to the way that the water sits in the sand versus how the water sits in a soil like this, the pressures don't rise in the same way in this as they would in sands from like an ocean wave, for example.
Okay.
We think that these are mostly just soft due to the fact that they were deposited fairly recently and don't really have a lot of time to get stronger, because a lot of times soils will get stronger if they can consolidate, but these don't really have the opportunity to at least we think so.
Yep. Okay. That makes sense. Thank you.
Is the difference between sand and mud the particle size?
Yes, but there's a lot of intricacies to that. So, but basically it comes down to, if we can get to the most technical sense of this, sands are what we call inert particles. So the water just kind of hangs out with the sand. Whereas when you have like muds and clays, the water actually binds onto the clays. And so it actually has, like, if you think about it, we like to think about it as like little pillows of like water hanging out around our clay particles. So that's part of the difference.
I think that's it. You can give our speaker another round of applause.